Hello, good morning all. Today we shall go through how decision tree, how really it works, underlying concepts. So to begin with, I have taken data points. Typical decision tree handles the classification problem. So I have taken data points. Red, you can consider say no for any classifications, or probably green one you can consider as a yes. X0, X1 are my uh, features. So for given x0 and x1, my classification data points, red and green ones, these are my initial data points, the training sets for the AML, the data classifications. Now x0 is in the x-axis, x1 is in the y-axis. This is the 0th point, and every lines are about 5 points on the scale. Now to begin with, how do we place this data points in our decision tree? So let's start with first one. This is my root node. So to start with, I'll have 10 10 data points that is classified to the green, and 10 data points which are classified as red. So this is my root node. Let's say I put these conditions x0 less than equal to -12, whereas x0 is one of the feature. So if you take it x0 less than equal to -12, this is your 12th point, is -10, -15, this is my -12. So anything less than equal to, right? So these are the dots which are coming under less than equal to -12, right? So when the condition is true, then I have my 4 red data points which are coming under the left child of the root node. Now this become a leaf node because I don't need further classification, so I can stop here. I can always classify this as coming under red. Okay, and any data points which are going greater than -12, that would go to the right. So let's say if you take it here, in this case, all these data points would go to the right, right? So I come up here. So I am left with now how many data points? 10 green data points as usual, because none of them fall under these conditions, and 6 red points because 4 red points are already classified under the left side leaf node. So I have 10 green points and 6 red data points. Now let's say I choose this condition, x0 less than equal to 9. This is the x0 feature, which is value less than equal to 9. So x0 less than equal to 9 would go this side, and x0 greater than 9 would come on the right side. So for the convenience of discussion, let's take x0 greater than 9. So if you take x0, this is your x0 axis. So anything greater than 9 is any data points falling on this side. Remember, it is greater than 9, not greater than equal to. So these are the data points which would fall under this leaf node. These are the 4 data points. So I'd consider this is the leaf node number 2, right? Let me name this one as a leaf node number 1 here. This is the first one we discussed, and this is the leaf node number 2. So we could classify, these are also another red data points, classification as a red data points. So, and I am marking it as 2, right? So another case is x0 less than equal to 9. So these all data points fall under x0 less than equal to 9, where I have 2 red dots, right? And I have 10 green dots still, and they are yet to be classified because they still have randomness. They have mixed data sets. Now let me put another condition, x1 less than equal to 9. So if I put this condition, x1 less than equal to 9, this is my x1 equal to 9 line. So x1 less than equal to 9, anybody coming, they come under the left child of this node, right? So these are the data points, if you take it, which are x1 less than equal to 9. These are the data points. Let's call it 3, leaf node 3, because all are green. they all fall under leaf node number 3, right? So these all are classified as green data sets, right? And then anything greater than 9, similarly, if you look at who are left, anything greater than x1 greater than 9, these are the two data points that are left now. These are the data points which are left. So I can consider leaf node number 4, right? This is a leaf node number 4. So this is how the decision tree, it's a very fundamental binary tree. If you look at the data are so randomly placed, it's not it's quite randomly placed, or you can call this data has very high entropy, or because of which it's very difficult to classify with using any linear you cannot quantify, you cannot materialize this problem statement using any of the linear solutions. It cannot fit into any linear equations. So that is why this classifier problem has been defined. This is how the deep learning, the decision tree learning would try to classify the data points to, in this case, to red class and the green class. All right. So let's say this is how I train. I made my decision tree. Now I give a real data. Let's say take an example. This is my real data, which is 15.7. Okay. So if you put this now 15, which is greater than 12 minus 12, it will come under this line. Then you will see that it is x0 greater than less than equal to 9. No, this will come under here. And then it is naturally falling to the number red line. So this will be tagged as red now. So this data points will classify under red. All right. So this is once the tree is built, then you can place any data point. Let's say you can take a data here, probably data here, probably data here, based on the based on the uh, based on the decision tree table, data binary tree, it would classify your data point. There is another visualization, a beautiful artist way of looking at the visualizing the decision tree, how it works. If you look at your all the data points, if you look at there are greens, yellow sets, like, multiple yellow sets in the way same way there are multiple red data sets, and similarly green and your let's say pink or green or let's say light yellow or dark yellow, or it white is, and all those are all the way they have the decision tree has broken. And all of you know that that should be a great conditions by which that you should decide in such a way that the tree height doesn't increase so much. All those conditions also we should satisfy. Okay, so this is up to now we discussed how decision tree really classify a given set of data points which is very random in nature. Okay, but I have left one point, how this really, what are the decisions, how these conditions, who derive these conditions. So we'll come to that point now. All right, so next I want to give a visualization of the same data points which I took it. If you look at what it did, it's random data points, it has classified. If you look at, it has taken as something called green zone. These are all green zones, and the rest all are kind of red zones. Okay, so typical, it has classified the same way as I was talking. Here it is a multiple classification, so it has multiple class, more than two classes. Here it is two classes, so it's a green class and it's a red class. All right. Next, this is going to be busy slide. Keep an eye on our main objective is to define what should be my condition at each of the node. So coming to the crux of the decision tree making. All right. So as I said, there could be many conditions. Now we have to apply machine learning concepts. We have to apply certain information theory concepts by which we decide what should be our conditions. All right. So let's say I have two conditions. Now there could be many sets of combinations possible, but let's say I'm taking two conditions. All right. So x1 less than equal to 4, that's the x1 feature set less than equal to 4, or x0 feature set less than equal to minus 12. Let's see which one choosing is better. Okay. To start with, let's start the concept. There is something called entropy. The definition of entropy is the entropy value is derived like this. It's a probability of that class, right? Ith class, and then logarithmic of that probability. When you multiply these two and then take the sum of all of them, sum of all of the classes. Okay, for all the classes, you sum them up. That would be the entropy of that decision. Okay, so the decision when you take it and when you get the set of data points, the entropy of this set of data points is derived using this equation. Similarly, entropy of taking the right child of this node, the entropy of this we have to find it out. So that way we try to find out entropy, and from there we'll see how to find information gain, and then we take the decision whether should I go for this decision or should I go for these conditions. All right. So let's take x1 less than equal to 4. If you take x1 less than equal to 4, look at this x1 less than equal to 4. Anything below these points are considered x1 less than 4, right? So in that case, I have 8 greens, right? If you look at a1, a3, and your 4, 3, 7, and 1 equal to, right? So total 8 data points. So this is 8 greens, I get it. And how many reds? 1, 2, 3, 4, right? I am getting 4 reds. X1 less than equal to 4, I am getting, sorry, 6 reds. 1, 2, 3, 4, 5, 6. 6 reds I am getting here, right? So, so now if I take x1 greater than 4, similarly greater than 4, if I go above, how many green blues I am getting, greens I am getting? It is 1 and 2. Remember, it is x1 greater than 4, right? It is 2, and red I'm getting 4. 1, 2, 3, 4. So 4 data points, right? So then similarly x0 less than equal to 12, right? If you take less than equal to 12, so how many red? 4 data points, right? Here 4 red data points. Greater than equal to 12, right side if you take it, all 10 greens are up here, all 10 greens, and my 6 reds are up here. All right, so now we got the data points which are labeled as red or green. And let's find out now the entropy. What is entropy? Probability of that class into logarithm of probability of that class. Now, what is the probability of green class in this data set? That is 8 divided by 8 plus 6, right? It's 8 by 14. So 8 by 14 is nothing but 0.57. Similarly, what is the probability of red class? It is 6 by 14. So that is 0.43. And if you apply the entropy equations, that probability into logarithm of probability, right? Similarly, this probability into logarithm of probability. So using this, I find the number, the entropy number is 0.99. All right. Similarly, we can calculate for this one. If you look at, I have 2 green points and 4 red points. So what is the probability? 2 by 6, that is 0.33. Similarly here, 4 by 6, 0.67, right? And if you same entropy equations you put it, then you will get value 0.91. Same way you calculate for the 4 red, because 4 red means probability is 1, as green nothing is there, that's a probability is 0. So I got a 0 value here because logarithm of 1 is 0, and whereas here 0.95 because 10 greens are there, 6 reds are there, so 10 by 16 it should be 0.63, and 6 by 16 should be 0.37, so that would be 0.95. So I have now derived entropy of each data set on the left as well as right for the two conditions, right? And the root node, the entropy value is 1. Why? Because I have equal number of red class points and red data points, and equal number of green data points. So probability is 0.5. So both probability are 0.5. So if you put in these equations, that would come out to be 1. All right. So with this, now I know the entropy if I take this decision versus this decision. Now I have to find the very critical point that is called information gain. So information gain, the concept is, it is the entropy of parent. Who is the parent here? Here, right? Entropy of parent minus sum of weighted entropy of the child. Weighted entropy. So I have to apply the weight and the entropy of the child. Entropy of the child is what? This is the entropy of a child, 0.99, 0.91, 0.95, 0.0, right? And weighted entropy. So let's take information gain for 1. So I have to go for information gain for 1. So in this case, this is my parent, right? This is my parent entropy, which is 1. In this case, this is 1, right? And then weight. How do I calculate weight? The ratio of the number of child elements, right? The child data points with respect to the parent data points. So how many child data points I have? Here 14, right? 14 data points. 8 plus 6, 14, right? And total number of parent data points is 20. 10 plus 10, 20, right? So 14 by 20 into entropy of that data sets, that is 0.99. Same way, minus, again, this is sum of all, right, for all the classes. So you have to go on the left as well as on the right. So if you go to the right, now 6 by 20, why 6? 4 plus 2 child data points, whereas 6 by 20 into the entropy is 0.91. So then I got the information gain as 0.034. Similarly, you can calculate for IC2, which is for these data points as well as these data points, right? It is 1 minus 4 by 20 into 0, because 4 child data points here. If I took the decision as x0 less than equal to 12, and minus 16 by 20, because here I have 10 plus 6, 16 by 20. 20 is the total number of data points at the parents, into 0.95. 0.95 is my entropy for these data sets. So that result comes out to be 0.24. Now if you compare, Ig2 is higher than Ig1, right? So information gain 2, if you selected the x0 less than equal to 12, the information gain that you received is higher than this conditions. So which condition you will select? It is the condition number 2 you would select, because this should give better information. Your better classification would happen, because higher the entropy means higher the randomness. So higher information gain means lower the randomness. So that is the reason we go for information gain 2 here, which is greater than the information gain 1. So this condition will be selected up here. All right. Now I would touch upon another concept here. So this is, if you look at, this is one way using the entropy, you had found the information gain. The very similar concept, you can use the Gini index, or maybe you can use the misclassification error. If you go for Gini index, what you do is the formula just changes. It is the entropy has this formula, whereas Gini has this formula. If you look at Gini index, both are more of a parabolic curve, but whereas in Gini index, the peak goes up to 0.5, whereas entropy peak goes up to 1. For the probability of 0.5, the slope of the entropy is much higher than the Gini index, right? So that means your model would be more robust in Gini compared to the entropy. And there is another which is called misclassification, which the formula is 1 minus max pi. So that is the reason it is, the probabilities within this number, the probability of one class is higher than the probability of another class always. That's why the single probability will be taken. So you will get a linear line here. Similarly, you will get a linear line up here, because the probability of other class will supersede after 0.5. So that is why this linear curve is coming. So there are 3 curves. If you look at here, this is misclassification error. This is your Gini, and this is your entropy. And I have a gray line, which is more of a scale version of the entropy, so that we can compare. If you look at slope of entropy is higher than the slope of Gini, then the higher than which, and that in turn is higher slope is higher than the misclassification error. So based on the different data sets, you can choose one of the underlying, concepts of entropy or Gini or misclassifications, which shoots for you better for your data points, and classify better, so that your size of the tree is minimized and information gain is higher. Okay, so this is all about the data sets I was talking about how truly the using the decision tree you are able to classify the problem statements, and how what is the underlying algorithm for the data classifications. Okay, thank you all. Bye bye.